Now for section 4.4, polynomial and rational inequalities. So the content of this section is fairly brief, but we'll go through several examples. And what we're basically doing is using our knowledge about the graph of a polynomial or a rational function to solve inequalities. Since we're fairly good at graphing these things at this stage, and we can translate inequalities into questions concerning where graphs are positive or negative, above or below the x-axis, that's the plan. So if we have a graph of the function, then solving inequalities of the form f of x is less than 0, or f of x is less than or equal to 0, or f of x is greater than 0, or f of x is greater than or equal to 0. These are straightforward if we have a graph, and we know how to make graphs. As an example, let's look at number 7 from this section, which says, use the graph of the function to solve the inequalities. F of x is strictly greater than or equal to 0. And secondly, f of x is less than or equal to 0. A strict inequality first, and then a non-strict inequality. Well, if f of x is greater than 0, then f of x must be strictly above the x-axis. So we're looking for places where the curve is above the x-axis, not on the x-axis. That occurs for this part of the curve. That occurs for this part of the curve, excluding, of course, the x-intercept. The x values over here correspond to negative infinity up to negative 1. So negative infinity to negative 1, the inequality is satisfied. And between 0 and 1, excluding both of those endpoints. Looks like the function's undefined at x equals 1. It has a vertical asymptote at x equals 1. At x equals 0, it's defined, but the value equals 0, and we're considering the strict inequality. So we'll also take all x values strictly between 0 and 1, giving us that the inequality is satisfied on the interval from negative infinity to negative 1, open interval union, open interval 0 to 1, excluding the endpoints. In part B, we want to see where f of x is less than or equal to 0. The or equal to part will say, well, this time we're going to include intercepts. We'll include x-intercepts. Same graph, different question. For f of x less than or equal to 0, this is satisfied when f of x is below the x-axis or on the x-axis. That is, when y-coordinates of points are less than or equal to 0, y-coordinates are function values. Y equals f of x is the setting we're dealing with. So below the x-axis, that occurs for this part of the curve and for the right-hand part over here. This part of the curve deals with x values between negative 1 and 0. So we'll include everything strictly greater than negative 1, has a vertical asymptote at negative 1, so that's excluded. This time we'll include 0, include that right-hand endpoint, because it's a non-strict inequality, and at 0, the function takes on the value 0, y equals 0 at this point. So in this case, we include the x value of 0. On the right-hand side, this part of the graph corresponds to x greater than 1, not equal to 1, as discussed previously, vertical asymptote there, and unbounded on the right-hand side. So the x values solving this are the x values in the interval from negative 1 to 0, excluding negative 1 and including 0, parentheses versus square brackets as usual, union the interval from 1 to infinity, parentheses on both sides. Of course, you would never have a square bracket on infinity because that's not a number and that's meaningless. And a parentheses on the one side, one's not in the domain of the function. So there's a quick way to deal with inequalities, provided you have graphs. Of course, it'll be more interesting when we're given equations and we don't have graphs, but we can create graphs because we know how to do that now for polynomials and rational functions with certain limitations, but we know how to graph well enough to answer inequality questions. So we can solve, we'll look first at polynomial inequalities, solving these algebraically. We'll do the following. Write the inequality so that a polynomial expression f is on the left side and 0 is on the right side. So we'll be looking then at f of x is greater than 0, for example, or f of x is less than or equal to 0. We'll convert the inequality into something of that form and then do it like the previous example by considering a graph. Step 2, determine the real zeros, the x-intercepts of the functions. That'll tell us where the function equals 0, which is relevant. It may not be part of the answer. It depends on the inequality question. Use the zeros found in step 2 to divide the real number line into open intervals. Okay, we're dealing with a polynomial function here. So its domain is all real numbers. So we'll take all real numbers, partition it into intervals using the zeros of function f, as we did previously. Step 4, select a number in each interval, a test value, we've called it in the past, denoted C. Evaluate f at that number. Determine where f of c, whether f of c is positive or negative. If f of c is positive, all values of f in the interval containing c will be positive. If f of c is negative, all values of f in the interval containing c will be negative. Same kind of thing we did before. We could, with this information, then probably create a reasonably good graph of the polynomial function. But to answer an inequality question, we don't actually need to go as far as graphing. We do need the positive and negative information, and that we can get algebraically as just described. So let's look at number 26, where they wish you to solve the inequality x plus 1 times x plus 2 times x plus 3 is less than or equal to 0, algebraically. Okay, so we'll use those 4 steps. Step 1 is to write this such that we get 0 on one side of the equation, the right side of the equation was what was explained. So we've already got it in that form. We'll make the left side a function. Well, so we'll just simply set f of x equal to that product there. You want to multiply that out? No. We're going to try to factor it. Fortunately, it's already factored. So for step 2, we would factor the left-hand side, but this one is already factored for us. So we'll see where this function could be 0. We're looking for x-intercepts here. Of course, it's 0 when any one of these terms is 0. So that would be x equals -1, x equals -2, and x equals -3. Listing them in order, in lesser to greater order, left to right as they appear on the number line, which is important because we're going to break the number line into intervals using these. So listing them in order. First, x equals -3, second x equals -2, and third x equals -1, simply stating where the function equals 0. The order doesn't matter, but get in the habit of listing them from lesser to greater order, because in step 3, we're going to divide the domain of the function, the real number line, up using those numbers. So we'll take the interval from -infinity to the first number in the list. -3 would appear first. It's the lesser of the 3. -infinity to -3. Then -3 to the next one. -2 is the next number when listed lesser to greater. And then -2 to -1. Remove that one. And then -1 to infinity, giving us 4 intervals. Think of the real number line as a stick. If you break a stick in one place, you get 2 pieces. If you break a stick in 3 places, you get 4 pieces. So we had 3 zeros of the function, and we got 4 intervals resulting. So we'll consider for step 4 where the function is positive and where it's negative. Take those intervals, choose a test value. Pick a number, any number in these open intervals. For polynomial, these will always be open intervals. Let's pick -4. It's in the interval and it's in magnitude, it's small. Here, maybe -2.5, -5/2. I can't pick an integer out of this interval. Can't pick an integer out of this interval either, which is maybe the midpoint, -3/2. Here, 0 is a natural number to use. Use 0 whenever you can because the arithmetic is easy. For example, if we plug -4 back into the function f of x, we'll have -4 plus 1, that's -3. -4 plus 2, that's -2. -4 plus 3, that's -1. I can multiply this out to get -6 if you like, or just simply observe, because this is the only information we need to answer the question which is asked. That's a negative. Negative times negative times negative. There's 3 negatives involved in the product. The product will be negative. -6 for numerical fans. But the fact that it's negative is all that matters. Granted, this is easy to multiply out. Some of the others, the multiplication out is a little bit more complicated. None of these are particularly bad, but I don't care what the value is. I'm only interested in the sign of f of c. Negative here, positive here, negative here, positive here. Often, but not always, polynomial functions will alternate between positive and negative. It's got something to do with the even or oddness of these factors as a multiplicity, right? It's related, whether it alternates positive, negative, negative, positive. It's related to whether the function crosses the x-axis or simply touches it. And that's related to the even or oddness of these factors as multiples, leading to zeros of multiplicity, whatever, multiplicity, the exponent on that factor. But this is sufficient for us to answer what we need to know. And the question was, where is this function less than or equal to 0? It's equal to 0 at each of the endpoints. Less than 0 is where it's negative. Negative here and negative here. So we'll take this interval along with the endpoint, -infinity to -3, along with the endpoint, -3, because of the or equals to part. This factor is 0 at -3. Union, negative on this interval, along with the endpoints because of the or equals to part. Were it a strict inequality, you want this to be strictly less than 0, we'd lose all of the endpoints, of which there are 3. Remember, -infinity is not an endpoint. This represents something more subtle than that. And so f of x is less than or equal to 0 for these x values. So doing this algebraically, and this example makes it appear computationally fairly easy. Granted, this one was a little bit easier because the factoring was already done for you. If you can do the factoring, then it becomes very mechanical. And you simply go through and choose positives and negatives and answer the corresponding inequality. Okay. The following steps apply both to polynomials and rational inequalities. Previously, those 4 steps we stated were for polynomials. In a polynomial, we don't have concerns about division by 0, but with rational functions we do, so this will have to be dealt with slightly differently. We can solve polynomial and rational inequalities algebraically using the following steps. Write the inequality so that the rational expression, let's call it f, be a rational function, is on the left side and 0 is on the right side, and they're separated by some inequality symbol, greater than, less than, greater than or equal to, less than or equal to, one of those 4. So that the question then becomes, where is this function positive and where is it negative and where is it 0, maybe? We're totally equipped to deal with that. That translates into a where is the function above the x-axis and where is it below the x-axis and where are the intercepts, things we've done in the past. Step 2, determine the real numbers at which the expression f equals 0, that'd be the x-intercepts, If the expression is rational, find the real numbers at which the expression is undefined. That would be where we have division by 0. How are you going to do this? By factoring. Factor the numerator and factor the denominator. Nobody said anything about simplifying, though we might do some simplifications. We'll illustrate it with an example. Use these numbers found in step 2 to divide the real number line into intervals. Okay. Rational functions are going to be defined on the real number line except where the denominator is 0. That's where f is undefined. So those points get removed. And in the test we're going to do of positive and negativeness, we're also interested in where the function equals 0, as we were with polynomials. So you remove those two kinds of points from the real number line, then make the chart. Then choose a test value from each of the resulting intervals, and the test value will tell you positive or negativeness throughout those intervals, just as before. So the only difference in rational functions in inequalities and polynomials in inequalities is this stuff about where the function f is undefined or where the expression f is undefined, where you get division by 0. Those become important points as well. They're not even an issue if we had a polynomial function. So let's illustrate those ideas just with a few examples. Here's a rational inequality. Where is this? Less than 0. We would be interested in factoring numerator and denominator. Numerator is already factored. Denominator, we could factor it. This is a sum of two perfect cubes. We have a formula for that. Alternatively, we can determine when this is 0 without actually factoring. Hey, x cubed equals 1. This is 0 when x cubed equals -1. And that occurs when x equals -1. So we can actually find the relevant numbers without going through factoring in this particular expression. You want to factor it, you go right ahead. You're going to have to recall how to determine when or how to factor a sum of two cubes. But we had a formula at some point in the past. Okay, so we'll go through those 4 steps. First, express the thing as a function in an inequality. It was given to us in that form. Secondly, we're interested in where the numerator is 0. That's where the function is 0. That occurs when this factor is 0, that is x equals 2. And when this factor equals 0, that's x equals 2/3. So these are 2 points of interest. We'll take the real number line and remove these 2 points, along with where the denominator is 0. The denominator is 0 when x equals the cube root of -1. When x cubed equals -1, we'll have division by 0. That we can solve algebraically to produce the only real value of -1. So we have 3 points of interest in order, left to right. I guess it would be -1 first, and then 2/3, and then 2. These correspond to x-intercepts. This corresponds to a point where there's division by 0. Graphically, I bet you got a vertical asymptote of x equals -1. That we don't particularly need to solve this inequality, but it's true. So for step 3, we'll take the real number line, remove first -1, then the next largest one, then 2/3, and then the next one. So least to greatest. Remove those from the real number line. You remove 3 points and produce 4 intervals. That leads us to consider these intervals, take test values, and determine their signs. For example, -2 is in this interval. It's the smallest in magnitude number in this interval. It's an integer, so let's use it. We'll use -2. I'm going to plug it into the function here. So that will give us 2 minus -2. That'd be 2 plus 2 is 4. cubed. We'll get a 4 cubed from this, which is, by the way, 64, but whatever. I'm only interested in the sign of it. Plug -2 in here. We'll have 3 times -2 is -6 minus 6. That'd give us a -8 for this factor, a -8. Down here, we'll get -2 cubed. That's -8 plus 1 will leave us with a -7. Plug the number in, it produces these values. You want to simplify this, enjoy. It's, I think it's 256 over 7. Anyhow, it's positive. The magnitude I'm not interested in. The sign is all I'm interested in. And I can tell that by writing these factors out. It's a positive times a negative times a negative. That'll yield a positive, and that's what matters. Similarly, plug the other test values in. No need to multiply out. Go right ahead if you want to, but it's not necessary. All you need are the signs. Positive times positive. That one's negative. One negative sign. They're all three positive here. Positive. Negative. Positive. Positive. Negative here. So we were interested in when that function is less than 0, when that function is negative. That occurs here and here. So we'll take the union of these two intervals. And there's where the inequality is satisfied. Hey, what if it were not a strict inequality? What if it read less than or equal to? Well, then we'd include the zeros of the function, where the function takes on the value 0. So you would include 2 and 2/3 in that case, and you get a square bracket on the 2/3, and you get a square bracket on the 2. You don't get a square bracket on the -1. Why not, if it were an or equals to question? Because the function's not 0, it's not even defined at -1. Remember what's happening in terms of a graph. It has a vertical asymptote at -1. The denominator is 0. So don't just mindlessly put square brackets around things when it's an or equals to. It depends on the context. You can mindlessly put square brackets around things in a non-strict inequality endpoints if it's a polynomial function. But if it's a rational function, you got to think a little bit more. Some numbers are more important than others in terms of an equaling 0. These are certainly the 3 important numbers in terms of intercepts. That's the 2 and the 2/3. So if it were or equals to, those 2 would be included, but not the -1. The function's not even defined at -1. Another example, rational function. Okay, this one's a little more involved. How do you factor that numerator? I'll just give you a hint. There's how you factor that numerator. This one is, I don't know, it's just tricky. So that's a reasonable hint to give. We might find a root and then use that knowledge to do some factoring. There's something called Descartes' rule of signs that tells you something about the roots of this. But anyhow, the numerator factors is given here. So I don't think that's given in the book, but let me give that as a hint for our purposes. Where is this function greater than or equal to 0 is the context of this section. Part A, they actually say graph it. So this will give us some more graphing experience of a function. So this time we will produce a graph, and from that graph, we'll answer the inequality question. All right. So we'll follow the lengthy 7-step procedure from the previous section for graphing a rational function. Step 1, factor the numerator and denominator. Numerator can be factored by the hint. So useful hint, there's how you factor the numerator. Denominator, x squared plus x minus 20, 2 numbers that multiply to give -20 and add to give +1. How about -4 and +5? So it factors like that. Usual factoring of a quadratic over the integers using nice numbers. So we can rewrite the original function as the factored numerator is given here, divided by the factored denominator, which we figured out. So here's the original function factored. Let's graph that. The domain is all real numbers except -5, where this is 0, and 4, where this is 0. Denominator is 0 at those 2 points, so they are not points in the domain. And the domain is -infinity to -5. We had to throw -5 out, you know, the open parentheses deal, curved parentheses versus square brackets. -5 to 4, and then we had to pick 4 out of the real number line. So we've removed these single points, and this is the domain of the function. At 4 and -5, we have division by 0, can't be in the domain. Something might catch your eye. Can't you cancel these? Yeah, but if you simply cancel these and make no additional disclaimers, you've changed the function. Well, I want to cancel them. Let's just be careful about that. If we cancel the x minus 4s, we create this new function. If that's all we do is cancellation, this function is defined at 4. I get what? 4 minus 1, I get 3, that'd be 9 over 9. This function's 1 at 4. But this function is not defined at 4. Well, then this function doesn't equal that function because this one's not defined at 4, and this one is 1 at 4. If I plug 4 into this one, no problem. So we've got to explicitly write that this equality only holds for x not equal to 4. So this is how you verbally say same function everywhere. This one's not defined at 4 because of the division by 0. This one's not defined at 4 because it says so right there. So simply canceling and not including this, you're losing information and you're introducing a different function. Granted, it's a very subtly different function, but this idea will make Calculus 1 work in a certain sense. The first topic in Calculus 1 will be limits, and you'll deal with ideas like this. Different functions, but very, very subtly different. So we put this in and make them exactly the same. We need equality with what we're dealing with. So we now have f of x in lowest form. So for step 3 in the graphing procedure, next we'd find the x-intercepts by setting f of x equals to 0. If we look simply at the numerator in the original function, let me bounce back. The original function, here it is, had a numerator of x minus 4 times x minus 1 squared. So the numerator will be 0, looking just at the numerator, at 4 and 1, but we can't use 4. That's not in the domain of the function. So looking at the numerator and setting it equal to 0, that condition alone implies x equals 1 or x equals 4. 4 is not in the domain of the function, so we can't use it, and the only x-intercept is x equals 1. Additional observation, we maybe didn't do a whole lot of this in the previous section, but at x equals 1, because of the exponent of 2, this is a 0 of the rational function of multiplicity 2. So what that means is when we graph this, it's going to touch and not cross the x-axis at x equals 1. Just an observation that was part of the discussion in graphing in the previous section. So we'll make sure it behaves like that. And we're going to see that information come out of the chart of where is the function positive and where is it negative as well. Y-intercept, we'll plug in x equals 0, plug x equals 0 into the original function. It looks like you produce f of 0 is 1/5. So that'll give us the y-intercept of 0, 1/5 as a point. Vertical asymptotes. For vertical asymptotes, we set the denominator equal to 0 when we've expressed the function in lowest terms. In lowest terms, the denominator was simply x plus 5. There was also an x minus 4 there. In lowest terms, we lose that and pick up the statement x is not equal to 4. Let me go back to the previous slide. Here's the function I want to consider. Where is the denominator 0? Where x plus 5 equals 0. And that's the only concern. Over here, well, granted, the denominator is 0 also at 4, but that doesn't count in terms of the function being in lowest terms. In lowest terms, we get something like this. So we ignore the x minus 4 because you look for vertical asymptotes when the function is in lowest terms. Do the cancellation, just do it carefully. Don't forget the little caveat about the fact that x is not equal to 4. So back to vertical asymptotes, the denominator in lowest terms, lowest reduced form, lowest terms. X plus 5 equals 0 is an issue. So x equals -5 is where we'll find a vertical asymptote. Again, you don't get a vertical asymptote at x equals 4. You had to consider the lowest terms version of the function. And we lose the x minus 4 factor in the denominator when we put the function in lowest terms. So a subtle difference between what happens at -5 and what happens at 4. Quite a subtle difference, really. But this behavior around the point x equals 4 is very much important for Calculus 1. So let's see, we found the vertical asymptote. I guess horizontal and oblique asymptotes are next. The denominator of f was of degree 2, and the numerator was degree 3 in the original rational function. So in that case where numerator is 1 degree higher than the denominator, n equals n plus 1 in the notation we had previously, that's when you get an oblique asymptote. So this one has an oblique asymptote. We'll have to do long division. Let's do long division on the version of f that is in lowest terms. So as opposed to dealing with the x minus 4 in both of these, which we equally well could do, we're going to deal with the lowest terms form of the function. The only difference between the function in lowest terms and the original function is the behavior at 4. Well, that's not going to in fact affect horizontal or an oblique asymptote. So we'll take numerator x squared minus 2x plus 1 and divide it by the denominator x plus 5 in reduced form. In so doing, we get x minus 7, multiply by x to produce an x squared, parentheses, subtract, we get a -7x from the subtraction, multiply by -7 to get the -7x, subtract, looks like we have a remainder of 36. The remainder term doesn't have much impact. It's the quotient here, the x minus 7, that gives us the oblique asymptote. So oblique asymptote of y equals x minus 7. They wanted us to graph it, so we'll have to include that information there. Had they only asked us inequality stuff, we could have ignored a lot of this asymptote stuff and dealt simply with this chart. But this illustrates graphing one more time for a rational function, an exotic rational function, because of that behavior at x equals 4. So we'll take the points we have above, which were -5 and 4. We'll divide the let's see, -5 and 4, and missed 2. We have that f is 0 at 1, not defined at -5 and at +4, so we use those points. I missed 1. The function is 0 at 1. Let me go back, and it's hard with these slides to keep up with everything. We had the function is as an x-intercept when x equals 1. At 1, we had the numerator as 0. Here's the numerator. Yeah, at 1, we had the numerator as 0. This is where we talked about it touching. So removing from the real number line, x-intercepts where the function is 0, that's x equals 1, and where the function's undefined, where the denominator is 0, that's -5 and 4, we produce this. All right, so 3 points, listing them in order, removing them from the real number line produces 4 intervals. We'll take a test value from each and determine signs. As before, make one little observation here. Notice when we go from the left side of 1 to the right side of 1, the function went from positive to positive. At 1, the function was 0. F is 0 at x equals 1. That was the x-intercept we were just talking about. And we said something about the graph touches the x-axis at that point. Yeah, it was positive, was above the x-axis. It must have gone down and touched the x-axis and then gone back upwards and remained positive on the right-hand side of 1 as well. Like I said, that information is contained in the chart. We got it from the multiplicity of the factor that produced the x equals 1. We had an x minus 1 squared in the numerator, and that evenness of that exponent tells you it touches the axis. So we know a lot of stuff these days, actually. So that allows us to produce a graph. I think with the information we have here, we could actually answer some inequality and questions based simply on this. But we see f is below the x-axis from -∞ to -5, where it's negative, and it's above the x-axis on these other 3 intervals. So we get above the x-axis on these intervals, and that's sufficient to answer the question that we had, but they wanted a graph. All right, so we'll deal with a graph. In so doing, we need to determine if those vertical asymptotes go upwards or downwards. Well, you know the positive and negativeness. We had a vertical asymptote at x equals -5. It was the only vertical asymptote. To the left of -5, the function was negative. Well, then it must go down to the left of -5. The notation we had introduced, there's a reference for you from the book, 10th edition of the book. Limit as x approaches -5 from the negative side of f of x equals -∞. That is, it goes down on the left-hand side of -5. The function was positive from -5 to 1. So when you get close to -5, but on the positive side of -5, the function's positive. Must be going up on that side. That is, the limit as x approaches -5 from the positive side of f of x is positive infinity. Usually don't put the positive sign on there. In other words, we can use the positive and negativeness of the function to determine whether it goes up or down, based on which side of -5 we approach, knowing it has a vertical asymptote at -5. And that was the only vertical asymptote. So this takes care of the vertical asymptotes. One more time, a little comment about the fact that this function is the function x minus 1 squared divided by x plus 5, provided x is not 4. Well, what does this other function here, let's call it g of x, this function, which is defined at 4, what does it do it for? If we took this function, which is the exact same function as the original function, except at 4, what was this one doing at 4? We can just plug 4 into this one because it's in the domain. That's why it's a different function than the original one. You can't plug 4 into the original one because you get division by 0. If we plug 4 in to this, we'll get 4 minus 1 divided squared, 4 plus 5. That's 9 over 9 equals 1. I commented about this earlier. But this function, nice and continuous at 4, just passes through that point, 4, 1. But the f function can't pass through that point because it's not defined at 4. So this is the subtlety. But the two functions are the same except at x equals 4. Well, what that means is the function f must have a little hole punched in it at the point 4, 1. And so we get the following graph. All right. So we know a bunch of stuff. We know horizontal asymptotes, oblique asymptotes. It had an oblique asymptote, not a horizontal asymptote. It had a vertical asymptote. We know where it's positive, where it's negative. We know it goes up on one side of that vertical asymptote and down on the other. So we know a bunch of stuff about the graph. This graph contains all that information. Here's the vertical asymptote, -5. We said it goes down on one side, the left side, and up on the other. We use the above, below the x-axis information for that. We said it was below the x-axis from -infinity to 5. Right, this part of the curve is definitely below the x-axis. From -5 over to 1, it's above the x-axis. At 1, it touches the x-axis, x-intercept there. At 4, it's got a hole punched in it. Like the g of x function, it wants to contain this 0.41, but we won't let it. It says right there, x does not equal 4 in this function that we're graphing. So the effect of that is to have a hole punched in the graph at that point. When you deal with limits, this is a common example that will be used in the limit setting in Calculus 1. And then to the right of x equals 4, it's above the x-axis. So this part is above the x-axis. This point's on the x-axis. This part's above the x-axis, and this part's above the x-axis. We have to deal with these two pieces here separately because of the fact that the function's undefined at 4. It came out of the computations. And here's the 0.01/5. It's a little hard to tell there, but that's the y-intercept. Again, I graphed this, by hand. I didn't use graphing software to graph it. I graphed it based on the information we had. The part B of the question was, where is f of x greater than or equal to 0? Not over here. It's above the x-axis and greater than or equal to 0. For this part of the graph, touches the axis here. That's included because it says or equals to. Got a hole punched in it there. We can't ever include 4. And it's above the x-axis over here. So that would include, in terms of x values, starting at -5 with an open interval, -5 over to 1, x equals 1, but you include the 1 because it touches the axis there, and this is an or equals to, so that still counts. Remains above the x-axis till we get to 4, can't include 4, function's not defined at 4. And then to the right of 4, the function is above the x-axis and the function's positive. So positive, 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 0 at that one point, positive, skip that point, positive, positive, positive. So the function's greater than 0 from -5 to 4, -5 to 4, excluding both endpoints for different reasons. Vertical asymptote over here, not in the domain. Hole punched in the graph here, still 4 is not in the domain. And then to the right of 4, the function is above the x-axis. So there's a graph, and there is a use of that graph to answer this inequality. We could have answered this inequality without the graph. We could have streamlined it and made the table that we made on the previous slide and actually got the information from that table, or 2 slides back. So I don't need a graph, but for the sake of illustration, here's a graph with all the information included. Okay, one final one, applied problem. Suppose that the government imposes a $1,000 per day tax on the bicycle manufacturer so that the daily cost C of manufacturing X bicycles is now given by C of X equals 80X plus 1,000. The average daily cost, C bar, is given by C bar of X equals 80X plus 6,000 divided by X. Average cost is cost per unit. X represents the number of bicycles produced. So average cost is always the cost function divided by X. For us, that's not entirely relevant. We just need to deal with the functions they've given us. But that's how this becomes meaningful in a business setting. How many bicycles must be produced each day for the average cost to be no more than $100? Average cost, here's the function, no more than $100. That's an inequality question. We want the average cost to be less than or equal to 100. Here's the average cost function. So what we want is average cost as a function to be less than or equal to 100. First, you must agree those words lead to this inequality. If you can't do that, then you're doomed. So now the math starts. So that's simply the translation of average cost, no more than 100. Here's average cost, no more than, less than or equal to 100. Dropping the units in the formulas. So we'll solve this inequality. First, we need one side of this equation to be 0. Here, neither side is 0. This is the first time we've seen this in our examples today. So how about we define f of x to be this average cost function minus 100, average cost function minus 100. We take the 100 to the left-hand side. That will produce this. Subtracting 100 from both sides produces this. We can get a common denominator. Treat this as 100x divided by x. Then we'll have 80x minus 100x. That's negative 20x. Denominator is x. There's a 6,000. Possibly pause this and convince yourself all we did was get a common denominator and simplify to produce this. Now this is what we would get by taking the 100 to the left-hand side. It would become negative and would simplify to this. So what we're interested in then is when this quantity is less than or equal to 0. We must have this stated in terms of a function less than or equal to 0 or greater than 0, a function compared to 0, because what we can find is where functions are positive and negative. So we've changed this into a question of where is this function negative or 0. This is not the average cost function. This is the quantity we're interested in being non-positive. So rewrite the inequality in terms of the verbiage of this section. Rewrite the inequality so that 0 is on the right-hand side and there's some function on the left-hand side. Let's call that function f of x. So that's what we've done. Previously, we started out by comparing functions to 0. Here we had to change it so that we had that comparison. So then we can work it with the techniques we have. Step 2, factor. It's already factored. Where is the function 0? Where the numerator is 0, that occurs at 300. If x equals 300, 20 times 300 is 6,000. So we'll get 0 in the numerator. So that's where an x-intercept is at x equals 300. The only 0 of the denominator is x equals 0. That means the domain excludes x equals 0. X is a number of bicycles, so certainly the number would have to be greater than or equal to 0, all else being equal. But to compute the average cost, the fact we got an x in the denominator, we can't have x equals to 0. So the domain is not x greater than or equal to 0 in this conversation of average cost. It must be x strictly greater than 0. So the domain of the function is x strictly greater than 0. It would have to be non-negative because it's a quantity. It have to be a whole number as well, since it's a quantity, to make actual sense. But certainly it can't be negative. And I can conceive of a factory that makes 0 bicycles, but then I can't compute average cost based on the algebra of the fact that we've got an x in the denominator and analyzing this function. We got to throw 0 out. So the domain of function f that is meaningful for this problem is the open interval from 0 to infinity. Granted, the function makes sense for negative x values as well, but it doesn't make sense in this context of counting bicycles. So we won't concern ourselves with the negative x values. It streamlines the work we have to do in terms of answering this question. Step 3 was to divide the domain of the function, in this case 0 to infinity, up by removing places where the denominator is 0, that's already done on the previous slide, and places where the function is 0. x equals 300. The function was 0. So we'll take 0 to infinity, remove 300. That's the only relevant point to be removed. And that just produces 2 intervals. If you want to include the negative numbers, it's meaningless. There's no need to. But we would get negative infinity to 0 as a third interval if we dealt with that. So because it comes to us as a cost function and an average cost function, x only makes sense when it's non-negative. These are the 2 intervals of interest. So pick a number, any number from 0 to 300. Suppose 1 is a reasonable thing to do. Pick 50. 50 easily divides 5,000. Doesn't matter. We get a quotient of 2 positive things. Function's positive. That's the information we need. Pick something between 300 and infinity. How about 301? Plugging it back into this function, we'll have, plugging it back into the f function, which I don't have in front of me, we get this quantity. We can peek back on the previous slide and confirm that. How about we take that as given? We get a negative in the numerator. I know there was an x in the denominator. The numerator must produce a negative 20. Anyhow, negative divided by positive is negative. Function's positive here, function's negative there. Question was, as we had translated it, where is f of x less than or equal to 0? That would be, where is f of x negative or 0? It's negative here, and it was 0 at x equals 300. So we get that f of x is less than or equal to 0 for x in the interval from 300 to infinity, including the 300. Their question was, how many bicycles must be produced each day for the average cost to be no more than $100? Well, the average cost, it turns out, will equal $100 when we have 300 bicycles. We had manipulated things so that we could apply our technique. That's where the 300 came from. But in terms of average cost, it corresponds to that average cost of $100 per bicycle. And anything greater than that will produce a lesser average cost. So average cost, you want to be less than $100 a bicycle, you need to produce at least 300 bicycles per day, was the units. And so there's a real world application that simply has to be reworded in a setting of f of x as a function. Here it is, f of x expressed as a function is compared to 0, greater than, less than, or whatever. We had to put it in that format to use our technique. And that's how you solve inequalities involving polynomials and inequalities involving rational expressions. It's simply a sign test. The fact that we created a graph in one of those, that's not entirely necessary, other than that was the question that we worked, but that's not necessary to solve the inequalities. For the inequalities, you just need the chart and the positive or negativeness. So that process is section 4.4. We'll move on in the next section and deal with zeros of polynomials, and we'll conclude this chapter looking at the fundamental theorem of algebra, which will require us to address some things related to complex numbers. Have a nice day. I'll see you in section 4.5. Bye-bye.